Hello, everybody. Thank you very much for joining our lunch seminar. If you haven't take a lunch box yet, please feel free to take one outside. My name is Mi Fang, and I'm a regional sales manager at DECTRIS for APAC area. So I'm really pleased to meet all of you here and listen to all the fantastic and inspiring talks. So it is a really great pleasure to have all our long-term laboratory and Synchrotron users here, and as well as our partners who integrate the detectors in their state-of-the-art SAXS instruments. So today, our first speaker would be Dr. Tilman, who is the product manager at DECTRIS, and welcome, Tilman.
One, two? Yeah, perfect. So, yeah, welcome from me as well. It's good to see all of you here. Let's go directly into the presentation. Did you show the agenda? You did?
No, I didn't.
No?
No.
So, I just give you can read the agenda yourself. So, this is structured as follows. We have two short presentations from Detectors. One is from me, focusing more a bit on a general introduction to DECTRIS and the Synchrotron detectors for SAXS. Then Markus will go into the detectors for SAXS in the lab. Then we have two presentations, also short, of our OEM partners, Anton, Paar, and Xenocs. And that is followed by two user presentations that are a bit longer. One from the lab, from Phillip Kohl, and from Jeng, which you all know as the host of this conference. So now let me start with the part on the Synchrotron detectors, HPC detectors for the Synchrotron and for SAXS applications, and what DECTRIS is actually doing. At DECTRIS, we develop and manufacture the most accurate, high-performance hybrid pixel array and electron detectors, and that we do to advance scientific research all over the world. So that's a bold statement. What we actually do is we manufacture the detectors, and we want to enable you to make these great achievements and really enjoy seeing all this progress you are making in the world of SAXS. DECTRIS originated, or these detectors initially started for being developed for protein crystallography, and that's where DECTRIS has a huge impact, as you can see here, or can learn from the protein data bank. In 2023, 80% of the entries of structures were made with DECTRIS detectors, and you can see that we have marginalized the other detector technologies, so the CCD only makes, by now, a fraction of 14% of the entries, roughly. We are headquartered in Switzerland, but we are, of course, distributing our detectors worldwide. We have subsidiaries in the USA and in Japan, and we have distributors that we work with in China, India, and Taiwan. And we have OEM partners, of which the two will present themselves. On this slide, I already said, we manufacture in Switzerland. And here I would like to point out on this slide that we are strongly R&D focused. So 2/3 of my colleagues are really working in R&D and covering all parts from software, system, and hardware, firmware development. We have all the steps that we need to produce the detectors as high HPC detectors in-house, also a clean room. And with that, let me directly jump to the detectors that we offer for the Synchrotron, of which we have all sizes, but we go up to very large detection areas and detectors that can frame very fast. And here you see on the left-hand side, the flagship detector that we currently have for SAXS is probably the EIGER2 detector, where you can have all the way up to 16 megapixels, and you can reach frame rates in the range from up to 700 to 4.5 kilohertz. The latest addition to this large area detectors is the latest generation of Pilatus 4 detectors that we launched last year, where you can get an active area at a larger pixel size but the same active area, so the same detection area actually, and with the 4 kilohertz frame rate even up to the highest detection area. Then we have one addition to this product portfolio that doesn't really seem to match, that is in the middle here, and that is the saloon detector, which will provide you up to 120 kilohertz frame rate, making it the fastest detector that is around. Has applications in XPCS, ultra-fast pyrography, wherever you want to go, scanning and time resolved. If you want to learn more about this, please come to the booth. Then very important for SAXS is we have specific solutions that are customized detectors to whatever your need is. And here are a few examples for wax detectors for SAXS, where you can see you cut out an edge or so to let the SAXS beam pass and have the SAXS detector behind. They often go into vacuum, and as you can see, they often also have a removable window that takes all the parasitic scattering background away. With that, I'm already at the end of my presentation. This is showing you the SAXS detectors that we offer and giving you a brief overview or summary of the specifications and advantages of the HPC technology. Yeah, thank you. And I hand over to Markus for the laboratory part.
Yeah, you can hear me with the microphone. Good. Thanks for joining the DECTRIS Luncheon. Some of you I've seen in the previous session, so yeah, it's me again, and some of the slides may even look familiar. Yeah, DECTRIS HPC detectors for laboratory SAXS. What are the key benefits of HPC for small angle X-ray scattering? The HPC achieves high spatial and angular resolution thanks to the small and sharp point spread function that we achieve in the direct conversion in the solid state sensor. And HPC also achieves high quantum efficiencies close to the absorption efficiency of the sensor material. Our EIGER 2 and Pilatus 4 detectors are available both with cadmium telluride and silicon. And silicon gives you high quantum efficiency for copper and gallium radiation, and the cadmium telluride is a universal detector material for more than 90% quantum efficiency for anything from copper to indium. So you can achieve 2- to 4-fold faster data acquisition for the high energies with the cadmium telluride. The HPC detectors do not have any detector background, and in addition to that, you can also suppress the environmental background. EIGER 2 and Pilatus 4 have 2 or more thresholds per pixel. So in addition to the low energy background suppression, you can also suppress the high energy background. That's exemplified here. With single energy discrimination, you see the high energy background, and with dual energy discrimination, you can subtract that and substantially reduce that by a factor of up to 5, which is particularly beneficial for CD-SAXS with long measurement times, weak signals. And the hallmark feature of HPC technology is the wide dynamic range. Yeah, you see here an example with the direct beam on the detector. So you have an I0 measurement simultaneously to the SAXS data acquisition, thanks to the more than 6 orders of magnitude dynamic range. For laboratory SAXS, we have the EIGER 2R detector series. These are not only SAXS detectors, but also VAX detectors. So the EIGER 2R 500K, for instance, is used as a VAX detector. And the large detectors offer wide Q range and fast measurements. From the small pixel size, you get a high angular resolution, 75 micrometer pixel size. The dual energy discrimination allows for low and high energy background suppression. And with the high count rates per area, you achieve wide dynamic range. Pilatus 4 is now new to the game. with a pixel size of 150 micrometer. And Pilatus 4 detectors offer large area and a wide Q-range coverage. So how does this compare to the EIGER 2 detectors? EIGER 2 detectors are our high-end detectors with the smallest pixel size, the highest count rates per area, and the widest dynamic range. And what Pilatus 4 brings to the game is that they make large area even more affordable than EIGER 2. So in summary, hybrid pixel technology gives you high quantum efficiency, high angular resolution, background suppression, and high dynamic range. And our EIGER 2 detectors are the high-end SWAX detectors, and Pilatus 4 detectors make large area even more affordable. And yeah, now I'm looking forward to the presentations of our two AM partners, Anton, Paar, and Xenocs. And we have Andreas Keilbach from Anton, Paar as the first presenter.
Thanks for saving me. Yeah, welcome also to this DECTRIS lunch seminar from my side. So I'm Andreas from Anton, Paar, and I'm happy to show you a little bit on our history that we have with DECTRIS. I want to briefly start off with the history that we have ourselves. So if you know Anton, Paar, we have quite a long history. We have recently celebrated our 100th birthday as a company. We started off as a one-man machine shop, and from there things developed, and the history of Anton, Paar is very closely related to small angle X-ray scattering. So it's still at our hearts. We started as the first company doing scientific small angle X-ray scattering, or commercial scientific small angle X-ray scattering in 1957. So there has been lots of developments that you see here over the recent years, and you see that the periodicity in between new developments becomes shorter and shorter. So stay tuned for new developments here as well. But what I also want to share is that a long time, or a long part of this history, we have already been traveling with DECTRIS, and we're very happy with the relationship that we have with DECTRIS. We looked today into some very old documents, and we found that actually we did the first implementations of DECTRIS detectors already in 2009 on our trusty old SAXS instruments that you see here. Some of these instruments, as you can still find in labs all around the world. So these instruments have been very reliable, producing lots of high quality data with the DECTRIS detectors. So this was a very successful relationship that we had with DECTRIS. And of course, now the story continues. These detectors are also implemented into our current portfolio. So the most recent detector that DECTRIS has been releasing is the Pilatus 4 detector that we have already integrated into our flagship SAXS.5 instrument that you see here. And my colleagues already had some time to play around with the detector for a couple of days, and we were just running some kind of reference samples with this detector to see how it performs in our instrument, and we have to say it performs really nicely. So here you can see some data that we collected on 120 nanometer silicon dioxide particles dispersed in water, and you see that we really get nice periodicity out of this kind of sample. And so this detector really makes a great value detector for a wide range of measurements where you don't need the super high resolution that you would get from an EIGER detector. So you can use this in applications such as small angle scattering, wide angle scattering, grazing incidents, and of course also in RIOSAX and things like that. And since we have a very long history, we want to continue that history and this very nice relationship that we have with DECTRIS. So we're happy to work also in the future with the DECTRIS detectors. We found this kind of logo that we had been doing for a little presentation already in 2014, but it still probably holds very true, and it's still very much valid. We are happy to work closely with DECTRIS, and we want to continue that. And with that, thank you for your attention. Please stop by our booth as well. We have some Austrian delicacies that we have still plenty of, so please stop by. We don't want to bring it back home. Please pick up your share of these and talk to us about SAXS, about DECTRIS detectors, and what we can do for you in your lab. Thank you.
Thank you, Andreas. So next, we welcome Alexandre Cheminal, who is a product development manager at Xenocs for more than 2 years.
All right, cheers. Well, Thank you, and thank you, DECTRIS, for letting us speak a little bit today about our nice systems that we are proud of, and introducing actually the new version of our flagship, the Xeus, aka Xeus Pro. So I'll take these 5 minutes to walk you through a bit into this new product that we are officially releasing. It features several interesting aspects that I will tackle, starting from things that are related to data quality. I need to mention that we have a new generation of Fox 3D optics with new optimizations that allows to have much nicer beam and higher intensity for high resolution collimations. And one of the main improvements that we have made to the Xeus is a completely new graphical user interface that is used to control the Xeus. So it's very intuitive. It's also very handy to use in combination with Exact. You have the very same layout and graphical interface, so it's very easy to go from Exact to Explore if you already know Exact, or to discover both if you are not a user at the moment. And it's very easy to play with those tools without being a specialist of SAXS. So we are here to talk about DECTRIS a little bit as well. So I wanted to do a bit of history as well. So we started with the Xeus 1.0 to introduce Pilatus detectors from DECTRIS. And it kept being around on the Xeus 2, from which we started to benchmark EIGER detectors as being like the highest end detector available on the market. So we kept using it on the Xeus 3 and now in the Xeus Pro series. And ever since we started using EIGER detectors, we've been using them in a so-called beam stopless operation, meaning that not only you don't have a beam stop on your beam, but there is no window, meaning there's no obstacle between your sample and the detector, meaning that your final data is less prone to artifacts, and you are so the quality of the data, you don't have to dopt on possible artifact or to rely on subtraction to get features very close to the beam, which is quite interesting. I need to mention, however, that we still have a removable window to protect the detector when potentially dangerous samples are used in the system. We have been offered the opportunity to test the Pilatus 4. Unfortunately, the fate made that I don't have data to present right now. So when I left HQ in Grenoble, the detector was still on the table next to the system, ready to be integrated. I hope we'll be able to test it, and I look forward having feedback from my application team on the possible applicative benefits of introducing possibly this new detector in our product range. So in particular, one of the possibilities is that the Pilatus 4 will bring more intensity given the larger size of the pixels, which could combine very well to reduce integration times with high power sources that we just have made available through our new collaboration with Rigaku, so that we can have in our portfolio a wide range of sources ranging from our in-house workhorse, which is the Xenocs, so solid target filament-based seal tube, through rotating anode sources, so namely the MM007 and the FRX from Rigaku, and also the well-known metal jet anode source from Exilium. So this is a wide panel of like power available in the beam and cost of ownership, so you can really find what you need within this range. So the Xeus Pro still features our large sample chamber, which allows you to bring very large sample environments in the vacuum. It's also by design ready for the XLR option, meaning that you can open a gap inside the structure and bring your own bulky systems into the beam, which is quite nice to to do very interesting state-of-the-art measurement. So because time is up, I need to conclude. So this is our team. So there's a lot of applicative scientists. So they are like nice people to talk with to discover new ways to use the systems and good interlocutors for you to find like peers to discuss with about the performance of our systems. And so thank you for your attention. And if you need more information, please meet at our booth. And I need to say we also have like some demo running tomorrow at our booth from 4 p.m. Thank you. And sorry for the overshoot.
Thank you very much, Alexandre. So next, we welcome the presentations from our users. The first is Dr. Phillip Kohl, who is an associate specialist at University of California from Santa Barbara. So Phillip been working with Yuli Li for more than 10 years. Welcome.
Oh, wow, okay, I'm using a microphone. Hey guys, my name is Phillip. I am stepping in for Dr. Yuli Li today, but I am excited to talk to you about the what we tout as the world's best in-house small angle X-ray scattering machine. So yeah, first I want to talk and say that the UCSB and DECTRIS partnership has a very long history. You can see in 2006, DECTRIS was founded and started selling their Pilatus detector in 2007. We bought a Pilatus 100K in 2010. In 2013, I got an internship. Fun fact, I got it because we had a Pilatus detector and Yuli needed somebody to help design a SAXS instrument, so I am forever thankful for DECTRIS for giving me a job. A couple years later, we bought the EIGER 1M. Another fun fact, this was the first EIGER sold in the US. One of the very first ones sold just in general. And then in 2020, we got the Bio-Pacific proposal to buy the EIGER 2-4M, which I will be talking about. And most recently, we bought a Muthin detector. We're repurposing our old 0-gen Rigaku Smart Lab for a high-energy molybdenum source powder diffraction. So I am here to talk mostly about Bio-Pacific MIP. So what is Bio-Pacific MIP? So NSF gave UCSB and UCLA a pretty large sum of money, $24 million, to buy cutting-edge instrumentation in order to characterize materials, anything that's biologically inspired or biodegradable. If you have that kind of research, you can use our facilities for free. So basically, they gave us a large amount of money. It hired staff and allowed us to develop all this instrumentation, and then we are treated almost like a small synchrotron, where users can either come in or mail in samples, and we will run them for you or help you with data analysis and writing and everything, and it's proposal-based. So this is a quick image of the team. This was taken during COVID. This is Yuli Li, who is the genius. And then there's me and Miguel. Together, the three of us are the workforce between our normal XRD lab and then also the Bio-Pacific lab. Miguel is more of the mechanical engineer, and I'm more of the computer engineer and data analysis side. So this is the CAD drawing as we developed it. So you'll see that we have the liquid metal jet right here on our Huber sphere. And then we have these scatterless slits that were actually developed by Yuli Li. I hear that at the Taiwanese synchrotron, they actually have the slits made by Yuli himself. So you might actually see them. And then there's our sample stage. And then inside we have the DECTRIS EIGER 4M inside a vacuum tube. It's on this carriage that allows it to slide back and forth from 100 millimeters to 2.4 meters away. So here is what it looks like after it was completed. You can see that unlike most systems, our system is actually not, the detector is in vacuum, however the sample itself is completely open. It allows us to accommodate much larger samples and more specific samples. So unlike industry where you have like a certain type of sample and you need to run it many, many times, we have multiple different types of samples that only need to be run once or twice, so we try to be more modular. Okay, so on the source side, we have the excellent metal jet. And if you don't know, instead of using a solid metal source, the E-beam hits liquid metal. In this case, it's gallium. And because you don't have to worry about melting the anode, you're able to increase the power load onto it and thus increase the flux. So in practice, because we have both a microfocus and a liquid metal jet, our liquid metal jet has about 20 times the flux as our microfocus on a normal day. On the other hand, we have the detector, which is the EIGER 2R4M. As you know, this is the best detector money can buy. And the big thing about the EIGER 2 is that it has 2 threshold suppression in order to lower the background noise. So you can see this was from their manual. You can see that this is a 2 threshold with 1, and this is a Pilatus 3 with 1 threshold. I decided this week to run that experiment myself. So on an actual sample, you can see that for very, very strong scattering samples, it doesn't matter maybe as much. But on an in-house system, it does. Okay, so this is for another sample that was run for 30 minutes. If this is a user sample, and that's the buffer, suddenly the dual threshold kind of matters. So you can see here that this is with only 1 threshold, and this is with 2, and the data is noticeably cleaner. And it actually is something that's very important on a in-house system because we can't, unlike synchrotrons, which are only run for a couple of seconds, we have to run for multiple minutes. So running a sample is actually very easy for any X-ray scattering experiment. However, making sense of the data and increasing the throughput is the challenge. So that's kind of what we've been doing at BioPacific. So one of the first things I did was I coded a GUI to allow users to run their samples seamlessly. So basically, we can 3D print a sample holder to match your sample. You choose it there, you pick where it is on the grid, give it a Qmax, a sample name, and then it goes to this queue. If you want to manually do this, you can with other tabs, and there's also a data analysis tab here, which I coded basic RG fitting, spherical fitting form factor. But anyways, you can see right here that basically all you do is you click and run, it moves to the sample, aligns itself, and then this is a live imaging process of basically, here's the data in real time, refreshing 10 times a second, and then here's the integrated data. Some nice features about the detector is that it can take the direct beam. Because it has the ability to take the direct beam, I'm able to auto-align the system and also be able to do this data reduction very quickly. Yeah, so you can see that this is real-time data. This one's a hexagonal. These are blockopolymers, diblocopolymers. And this one's clearly in the hex phase, and then I'm gonna let it go to the A15 just so you can see a cubic sample because it looks a little bit better. Yeah, but basic functionality, able to zoom in, change the intensity, but yeah, here you go. So this is the nice thing about the source and detector itself is that it has a very high angular resolution. On our downstairs microfocus source, we are unable to resolve these 3 peaks in the A15 phase. Yep, so that's all there is to it. So you can see that it's very simple to run a sample. Here's a little bit of a data comparison for iron nanoparticles. You can see that the red one is our upstairs system. Sorry, I should say upstairs. Our BioPacific SAXS, and downstairs, this one is our previous generation SAXS. And you can see that the data quality of 10 minutes is better than an hour downstairs. Or sorry, at the other, and then also you can see, as I was saying, it's about 20 times brighter, where an hour signal to noise wise is about 3 minutes with the BioSAXS. So that was a comparison of in-house system versus in-house system. This is a comparison of SAXS versus Synchrotron. So you can see both of these were run for 1 minute. Now I am going to clarify that our brightness is nowhere close to a synchrotron. This sample did not need to be run for 1 minute at SSRL, but you can see that for both of them they were run at 1 minute, and pretty much all of the features in the SAXS, in the biopacific SAXS is also prevalent at SSRL. So there is users that previously had to go to Synchrotron that now can use the biopacific instrument as an alternative. This is comparison of SSRL versus SAXS for grazing incidents, and again, you can see that you can get structural determination of this perovskite crystal that matches pretty much all peaks match. So some other samples that I've ran in the last couple of months is mapping of diseased coral. So because of the increased flux, we're able to cut down the beam size. So I set the beam size down to about 150 microns here, and then just went in an array through the entire thing. Now granted, this was about 10 minutes each spot, and I did SAXS and wax, so it took about 2 days to finish, but it was done, and you can see clearly that it's a little hard to see, but this this like yellowish color diseased area is where the calcification is occurring, and the healthier regions are this amorphous part of the coral. Another thing that happened was we did temperature grazing incidents for, this is a liquid crystal elastomer that's cut in a way that when you heat it up, it coils. And it should be a video just so that you can see that as you go from 45 to 65 to 90 to 120, you go, I'm temperature cycling here, that you go from amorphous to smectic and back and forth. Oops. And another fun one, okay, so another thing that's nice about biopacific and also what we do is that we help users with data analysis and also training. So this is an example of a user that was able to form a diblockopolymer system, and from the parents, they used chromatographic separation to basically split it into multiple samples. So basically they took 16 parent samples and used fractionation to create a much larger phase space of 300 samples. And the pros of this is now suddenly you're able to create your phase diagrams much faster because you're able to generate many, many more samples. However, the con is that you have to then analyze every single sample. So I helped the user create a basic machine learning program where it just basically looks for the peak positions and then from the peak positions deduces what phase it is. And it's to about 96% accuracy. And then continuing with that, since I knew what phase, I also wrote some code to do line shape analysis. So what you can see here is that this is a hexagonal diblocopolymers, but you can see that the peak intensities are varying pretty largely here. Now with the sharp peaks, I hypothesized that the reason why some of these peaks are getting suppressed and modulated is due to the form factor of the channels within the diblockopolymer. So with just a simple 3-term, I fit the first peak, set an exponential decay due to TDS, and then try to fit all the other peak intensities due to the radius of the channel. And you can see basically it fits very, very well. Here is some basic output where you can see the d-spacing of like basically the 4 pi over square root 3 for this as a function of NMR's volume fraction. But something that's also kind of cool is that you can see that not only am I able to measure the domain spacing, but I'm also able to measure the size of this radius to calculate how much volume this fluorinated block takes within the sample. And then I was able to compare that to NMR, and you see that basically it matches NMR very, very precisely. So it's a cool thing just to show that you can gain a lot of information from SAXS, and you're able to use both Yuli and I's knowledge to help you with your data analysis. Lastly, we have a variety of sample environments. So Yuli is an amazing engineer, and if you ever need a specialty type experiment, we are more than willing to help you. These are some things that we have. We have flow cell capabilities, a temperature cell that currently can go to 250, but if we need to, we can make it go higher. We have shear, as well as microfluidic devices available. So yeah, I lastly just want to thank again our industrial partners. Thank you to Exelum, and especially thank you to DECTRIS. I appreciate your guys' help and responsiveness when I have questions. And yeah, with that, I'll take any questions.
Thank you very much, Phillip. So any questions?
I had the impression.
Oh yeah, I forgot to qualify that. So unfortunately, in retrospect, we didn't really realize that. Yeah, the peaks are lower here. So the sample was taken 1 month later. I forgot to qualify. You can clearly see that the peaks are sharper here, so the resolution is better for SSRL. It's just that we synthesized it, ran it at BioPacific, and then waited a month, and we thought it would be just as healthy, but it looks like it did degrade a little bit. We're not trying to claim that we're definitely not better than Synchrotron in any way. We're just trying to say that you can get comparable data and that the key features in terms of the crystal determination can be seen there.
But you don't think that you exposed too long and destroyed your sample in Synchrotron?
I mean, it could be that, but I think, unfortunately, I don't know, the user ran it, but I trust their work, so I do not know. No, this is raw data. This is not background subtracted. Yeah, but I mean, if you look at like this peak, you can clearly see that it gets definitely stronger.
The
yeah.
flat background.
Oh yeah, I get it. Yeah, I see what you're saying.
Solvent, solvent may not be the same.
Yeah, then it wasn't solution scattering, but okay. Yeah. Sorry about that. Yeah, I think it's just degradation. It could be due to very long exposure times. I can agree with that, but it also could just be that the sample aged over time.
Okay, so I guess because of time reason, then we will, if anybody has any questions, please feel free to discuss with Phillip later, and then let's thank you, Phillip, again. Yeah, our final talk today for today's seminar is given by Dr. User Jeng. Dr. User is from NRCRC, and he is in charge of TPS 13A, the amazing BLSAX beamline. And probably many of you have been seeing already saw the posters from his beamline yesterday. User is also our host for this fantastic conference. So welcome, User, and thank you very much.
Thanks for the kind introduction. I'm now a guest. Okay. So I actually have bought a detector long ago, back in 2010. And, okay, sorry, it's a bit. This is our design for the TPS 13A with 2 detectors in vacuum. That's the original idea. So they can move back and forth and go to anywhere you want in the space. And then we start to talk to DECTRIS people. Well, you want to have 2 detectors. You have to have light pass through the first detector. So we request, can you make a hole here? It takes 2 years to get it through. Finally they say, okay, we make a hole for you. So that's the first hole detector. But nowadays you get any kind of cut you like, okay. But that's the beginning back in 2016. And then that's Stefan's, we discussed with Stefan, okay. Then later on we realized this hole here, and then icon 1M, and then icon 9M at the end. Okay, next is we realize these spin lines, and with the help of sit here, Nicholas. Last time he made the special solution for us, including all the detector name and 1M, and also the special box here. And it takes Sasha to come to NSRC to realize it. It works, okay? So that's the detector works in vacuum. I would say that, of course, detector sometimes fails. But you get the online support. That's what we work with Daniel in Swiss. We work together to fix some part of it. And then later on, also the Francisco and Takeyoshi-san will come, and on site we fix it for the final recovery. So we have temporary help and no final help. So this is quite good together to work, solve the intermediate problem then and the final problems. Okay, but I would like to say that I think DECTRIS does its job to bring us the very good low noise detectors. But the users do the corresponding part. We have to put the detector in vacuum to reduce the scattering noise. So both have to reach and to make I will skip this, just instrumentation, okay. So both detector and also detector environments has to match to bring the nice data in the high Q, which very often was blocked by the air scattering. So with the detector in air, in vacuum, we get this kind of quality of data. So now we have two detectors work together and get this set of data in one measurements. So this allows us to combine all the global structure and also the log structure, including the loops for putting in solution. So this now, you can see the details with this detector system. Okay, so I think I would not say too much to save some time. This video can be played? Okay, but that's why I mean at the beginning, dancing of two detectors in vacuums. So with this, user can really operate the two detectors outside the end stations. But this just hardware. If you want to make it really works, you need to have software to combine all the two detect data in one data processing. And this would we have also accomplished this. So when users operate this detector system, all the data processing in one protocol under one Windows. So you automatically got SAXS and WEX data merged and background subtracted, and then come up with the data sets I showed you. So users just feel like they are operating one detector and doing one data reduction. No complicated merging process.
Pero llegaste
Taiwan species. Take the opportunity to show our Taiwan special. The Hinoki giant tree in Taiwan. Okay, I think I stop here. Okay, some few words following these films. Working with DECTRIS is really a pleasure. I mean, we really, if you have some novel or crazy idea, they don't reject at the beginning, okay? Anyway, so, but it looks like they can provide the matching, matching solution at the end. So I hope in the futures, they also can provide matching solution for the detector price. Okay. Thanks for your attention. Yeah.